I and Sumin will present together to you this webinar. Actually, this is a second part of Steel Division 9 webinar for steel cleanliness. In the first part, presented by Professor Bob Tuttle a couple of weeks ago, the different practical aspects of this problem were discussed. That discussion showed that steel cleanliness is continued to be a real challenge for steel foundry businesses. It costs a lot of productions and strong effect on casting property. One of the main practical problems how to evaluate steel cleanliness. Sometimes our simple observation of steel quality using metallography does not indicate any troubles. Nothing seems to have changed in our technology. However, suddenly we got severe problem with casting quality. Sometimes at the same foundry, cast one type of steel has no problem, while the other type of steel are more sensitive to defect forming. Sometimes when we use the same ladle, part of casting has high quality, however other part poured from the same ladle are needed more job to reveal. And more importantly, steel cleanliness problems so random and sporadic that sometimes we even cannot say about trend which we observe. All these problems clearly indicate that we need to have a powerful tool for statistical evaluation of steel cleanliness in our industrial practice. If detailed data will be in our hand, we can predict the possible problems and to develop efficient processes. Today, I and Sumin will talk about a novel method for evaluation of steel cleanliness based on automated SEM-EDX analysis. But at the start moment of this webinar, I would like to say for steel foundry community that this tool is not only for academia or research organization. In last decade, this method became a routine tool for day-to-day operation in steel mill, and Sumin will show you many practical examples. Yes, an automated SEM-EDS analysis is not used in foundry practice yet. However, I will show you today how this powerful tool can be used for steel casting production. Our webinar will consist of several parts, and we will share our presentation. Before, let me briefly discuss why we have steel casting quality problem caused by non-metallic inclusion. Casting from all alloys have more or less non-metallic inclusion. For example, in aluminum alloys, non-metallic inclusion presents as that aluminum oxide, which could have shape as an individual particle or create field, even bifield. Some exogenous inclusions come from flux. In copper alloy, non-metallic inclusion mainly present as copper oxide. It's interesting to mention that in cast iron practices, we consider that some inclusion can be very helpful because they promote graphite nucleation at lower melt superheat. This blocks cementite formation and blocks so-called chill zone which decrease machinability. Of course, exogenous inclusions like slag, sand, or some endogenous inclusions like magnesium sulfide are very dangerous in ductile iron. However, if we will ask aluminum or ductile iron foundry metallurgists about the main industrial problem experience, it will be mentioned porosity or other so-called casting feature, and non-metallic inclusion will be in note on the first place. However, this is not a case for steel foundry. Here we experience with all kinds of non-metallic inclusions. And the main reason for this is a difference in melting process temperature. We can divide the origin of non-metallic inclusion in steel to endogenous, which occur within in situ the metal as a result of different chemical reactions. Typically this inclusion is small at forming. Interesting that many of endogenous inclusions come from our deoxidation practices. However, we cannot cast steel without deoxidation to avoid severe gas porosity. Sources of exogenous inclusions could be lining, mold, and each size varies greatly. We have also something special in steel practices, so-called reoxidation inclusion formed at last stage when steel poured into the mold. Reoxidation inclusion in cast steel could be a combination of both types of non-metallic inclusions. Let me briefly to show the thermodynamical nature of non-metallic inclusion. As I said, in steel practice, we have very high temperature. And at this condition, many of the metals which is not reactive at room temperature became very aggressive, and the thickness of oxidation reactions depend on affinity of specific element to oxygen. This diagram on the right side to show Gibbs free energy, the vertical axis, of different oxidation reactions. All these numbers are negative. It means that we have possibility, thermodynamical possibility of the oxidation reaction. A red line show oxidation of iron, and all elements below this line will oxidize firstly. Silicon, manganese, titanium, chromium, all of these elements will be oxidized during melting at very low partial pressure of oxygen, carbon dioxide, or vapor in furnace or mold atmosphere. As a result, we have a beautiful gallery of different type of non-metallic inclusions. It could be aluminum oxide, dendrite shape. It could be complex, like this presented, as a manganese sulfide gray, which grows later around aluminum oxide. It could be complex inclusion containing calcium, aluminum, magnesium, or could be pure like manganese, aluminum oxide spinel, or titanium nitride having cubic shape. Let me show you three-dimensional shape of non-metallic inclusions revealed by deep etching of metal matrix. This picture are from our with Professor Li Feng from Beijing University recently published article about inclusions in continuously cast slab. Alumina has tendency to form dendrites, which easy to be aggregated in large inclusions. Some inclusions has original shape. Some inclusion like calcium modified. It could be complex inclusion. Most importantly, that these inclusions, calcium modification transforms solid to liquid inclusion during processing. A liquid inclusion gallery is interesting maybe for academia professor of metallurgy. However, exogenous inclusions are huge headache for foundry metallurgists. Majority of macro-inclusion in carbon and low alloy cast steel are reoxidation inclusion. Primary oxygen source could be air during tap of metal, in ladle. It will be oxygen source during holding steel in the metal from the open surface or under slag with iron oxide concentration. We have oxygen sources during mold pouring, and also oxygen sources could be as a contact of liquid steel with solid mold materials. What we have in result? We have in result two types of inclusions. One could be located on the surface, and this picture was taken by me with permission one metallurgist. You can see all these marks. It could be defectly revealed. It's like kids' graffiti casting. So this inclusion, surface inclusion, clearly visible, is easy to indicate, however, require extra finishing. Another type of defect is subsurface defect. It's not visible, hard to detect, and they reveal during machining and create machining difficult and cost our foundry business also a lot, because sometimes we need to have rejected casting with partial cost of pre-machining. Now, after brief review of foundry cleanliness problem, let me pass my presentation to Zumin. Zumin, please.
Okay. Yes. Thank you, Simon. Good morning, everybody. So here I would like to give a brief introduction of the automated SEM-EDS technology for non-metallic inclusion analysis. So, automated inclusion analysis, for the inclusion detection, there has been quite a few different techniques. And as you can see on this slide, there's a chart showing on the different length scale, there could be different techniques to detect the inclusions and measure the information of inclusions. So usually the ultrasonic analysis measures 100 micron and above size inclusions or defects. And then there's other optical methods that can detect on the length scale of a few microns and above. And the automated electron beam inclusion analysis technology can really cover from sub-micron size to really over to 1 millimeter size inclusions. So what do we really need to get is the size and distribution, the quantity, and the shape of inclusions. And traditionally, these other methods do not provide the composition of inclusions. And without knowing the composition and the size and everything else, it's really hard to really control the inclusions. And as we know, the inclusions can impact the production process, and it can have a negative effect on the product quality, as Simon just described earlier. So here our goal is to look at how we can use the automated SEM and EDS technology to measure inclusions and review all this information. Okay, so next slide. Okay, so here I would like to give a brief introduction of the SEM and EDS technology. So the SEM is a scanning electron microscope. EDS is the energy dispersive X-ray spectrometer. This schematic shown on the left side of the slide shows the electron beam can come from a column. So the electron beam hits the sample on the bottom. It generates signals. So usually it's a backscattered electron signal. So you can measure take the image. Also, it generates characteristic X-rays. These X-rays will tell what the composition of the inclusions are. And on the left side, it's a unique design offered by the FEI company. It's called ASPEX Omega Max EDS detector technology. So the way it works is it has a much closer distance to the sample. So this omega angle, it's the solid angle. You can maximize the collection of X-ray signals. So that allows the whole SEM-EDS system to measure the inclusion information at a very fast speed. And we've done some tests in our company. We've seen that with the traditional design EDS configuration, which is on the right side, compared to the left side Omega Max detector, we can get 5 times faster data acquisition speed. So on the next slide, I will show you some more details on how it works. Okay, so here there's a nice picture showing ASPEX model 1020. This instrument is located at the Missouri University of Science and Technology in Rolla, Missouri. On the bottom, it shows the mechanism it works. So for each sample, the whole sample will be divided into different fields, because at a specific magnification, only a certain size of the field can be viewed in the electron system. So for each field of view, the electron beam will start search for inclusion. As shown here on the schematic, it shows several steps. As the first step, the electron beam will scan the background. And the second step is as soon as the electron detects an inclusion based on the image contrast, the system will automatically switch the magnification from a few hundred x magnification to up to 10,000 or higher magnification. And then the scan speed goes to a very slow scan speed, it measures the dimension of the inclusion by a, we call it a rotating quad algorithm. And then next, after measuring the shape and size of the inclusions, the EDS detector will take the X-ray signal, and it detects the composition of this inclusion. And this spectrum information will be sent to the database. So the database detects that this could be a manganese sulfide inclusion, for example, in this case. And then after the system is done with this inclusion, it will continue the search at a large step at a faster speed for the next inclusion. So what it measures is, as you can see, it measures the shape of the inclusion. It measures the size of the inclusion. It also calculates the area of the inclusion and the physical position of this location on that sample. And more importantly, it tells the chemical information based on the EDS signal. So how long does this take? Traditionally with traditional SEM and EDS technology, usually it takes a couple of minutes to just search and find the inclusion and then do manual analysis and then take the EDS chemical composition. But with this fully automated system, you can measure each inclusion at a speed of less than 1 second, and it's fully automated. Doesn't need anybody to operate. The machine will do the job. And by doing this, you can measure up to 10,000 inclusions within 1 hour and get all the necessary information to make a decision. Okay, so next slide. So after we do the inclusion analysis, what we get is a lot of data. So as shown on this slide, you can see a map showing the distribution of inclusions on the sample. Right, so as we zoom in, put a mouse on each feature, each inclusion, you can see the SEM image of this inclusion, and also it shows you the EDS spectrum along with the chemical composition. And a lot more information can be seen in the full spreadsheet as the system generates. Okay, and based on the large data set, we can do statistical analysis. For example, the statistical distribution of the size, the chemical composition, and we also use the ternary diagram to show the composition distribution, as you can see on the next slide. Okay, so here are some examples of the report template. Because usually the raw data itself, they don't have any value. Right? We only get value by presenting the data in the way that is relevant to our process. So we have created the template to present the data. The ternary diagram shows the distribution of inclusions based on ternaries. And these ternaries really tells the statistical distribution. So for example, it may not just be pure aluminum oxide. So like the first diagram shows, as we measure inclusions, they could be a combination of a calcium, aluminum, and magnesium. So by looking at ternary diagram distribution, it really provides insight information. Okay. On the right side, it also shows a breakdown of inclusions by chemical composition for each class of composition. These definitions can all be defined by the user, and it also shows the inclusion index, which is based on the total area of inclusion on the total area of samples. Okay, so these are just examples, and depending on the use cases, the report templates can all be customized. Okay, so next. Okay, so here we show some more detailed reports. Again, these reports can be customized based on the specific application needs. On the left side, it shows, we call it an extreme value report. What this report does is, based on the user's preference, you can generate a report by highlighting the largest 10 or 20 or 50 inclusions, or based on your own defined criteria. It will show you a snapshot of each inclusion for its image, spectrum, composition, and the size, the Dmax, Dmin, and area, and what kind of classification it belongs to. And on the right side, it shows some bar chart and a table to summarize the total inclusions and how many are each specific type of inclusions. So yeah, so just give you some examples here. So next slide. So we also realized that at some steel companies and even the users of a steel, they would like to know the cleanliness of the steel. Right? So if a steel is supplied to an automotive company or a medical device company, they would like to know the cleanliness based on some industry standards. So here we have a report template, the same large data set collected by the automated SEM-EDS can be directly reported according to the ASTM, like E45 standard, and the Japanese industrial standard or ISO standard. And lately, we have developed the German steel cleanliness standard, the DIN standard. So this will help the steel manufacturers or steel foundries to provide a report to tell the cleanliness level of steel. And the benefits compared to a traditional optical microscope is by using SEM and EDS technology, you can really differentiate the scratches, defects, and those non-real inclusions and give a more accurate steel cleanliness rating. Okay, next. Okay, so with this technology being developed over the last few years, in the steel mills, it has got a lot of adoption. So we have seen that in both the mini mills and integrated steel mills, the ASPEX automated SEM-EDS technology has been widely used in the various processes in the steel making. We have seen that people take samples from secondary refining, and they also take samples from the continuous caster. And also, when the steel slab or billet are casted, they can section samples from that and measure the inclusions. Or even at the end of the process, to finish the product by rolling, they can still measure stringers and that kind of inclusion data. So next, I will give you some real examples. In terms of the inclusion analysis implementation, on this slide, the picture shows the latest model of the automated SEM-EDS instrument. The motivation of doing inclusion analysis usually starts with problems in making steel, or when a new process is changed, it is necessary to do the okay. Sorry, I found there's I couldn't see my screen right now. Looks like there's a little bit computer problem. Okay, so maybe I'll just continue without my screen on. Sorry about that. Okay, so as we can see, the inclusion analysis is really part of problem solving. But over the long term, once the standard practice or corrective actions have been put in place, now it's time to do cleanliness steel inclusions monitoring. So even without a problem in the steel making process, now a lot of steel mills, they take samples in steel making process to monitor the inclusions, so they can take preventative actions to avoid some problems in steel making and the downstream steel quality. Okay, so next slide. I think the next slide shows an example of using inclusion analysis in a steel mill. And this report is published in a few years ago by some European steel companies. And back then, they have already started using some older versions of automated SEM-EDS technology provided by the ASPEX company. So what they have done is they studied the calcium treatment of the steel in the secondary refining process to try to optimize the steel treatment to control the inclusions. So what has been done is the steel samples were taken from the various steps in steel making process, and these samples were put in the automated SEM-EDS machine to analyze the inclusions. And the ternary diagrams are used to visualize the inclusions distribution. So based on that, you can see as the calcium treatment starts, as it continues, at the end of the treatment in the secondary refining stage, the inclusion populations and the sizes really evolve. And in the end, we can also see that after the steel is tapped into the tundish, it shows some reoxidation. It really increases the total population and the size of inclusions. So by doing inclusion analysis, it really helps to directly measure the inclusions evolution, and it allows the metallurgists to better control the inclusions. Okay, so I take the next slide as an example from Nucor steel in a mini mill steel making process. In this example, it shows, again, in a mini mill, the calcium treatment optimization. As we can see, there are these ternary diagrams, and on the ternary diagrams, it shows the a liquidous zone. That means the inclusions falling in those liquidous zones are liquidous inclusions. And for this specific example, there are a lot of spinel inclusions. And the spinel inclusions are usually very harmful for the quality of steel because they are hard, they're difficult to deform. So the goal here is to use calcium treatment at a Nucor steel to convert these hard spinel inclusions into liquid, soft inclusions. So by in this case, it shows that by optimizing the calcium treatment, they can really convert most of the inclusions to the liquidous zone. But without directly measuring the inclusions, what we can see is either the calcium treatment is not enough or it's overtreated. So if it's not enough, then there are still a lot of hard spinel inclusions. They can still cause the nozzle clogging or downstream quality issues. If the treatment with calcium is too much, so first, there's a waste of calcium, and second, the steel becomes really corrosive, and it can really corrode the refractory materials. Okay, so take the next slide. Next slide, does that show the testimonial from Nucor Steel?
That's right.
Yeah, so I think on this one, it shows that Nucor Steel actually, they have been using this technology so successfully. They put the automated SEM-EDS in all their flat products and special bar quality steel mills, and they are doing steel inclusion monitoring on a daily basis right now. Okay, so I hope that gives a good overview of the automated SEM-EDS technology and its implementation in the steel mills.
Okay, thank you. Now let me continue about application for foundry business. As I mentioned before, today automated SEM-EDS analysis is not used in foundry practice. However, I will show you right now how this tool will be very powerful to understand our casting problem and improve our technology. So I will give you a couple of industrial examples which we work with our industrial foundry partners to analyze situation, better to know origin of how the inclusion was born on the different stage of steel melting processes. So We typically start from sampling using special sampling, like submerged sampling from induction furnaces or electron furnaces on the ladle, on the stream, from the casting. So when we got this set of sample and using automated inclusion analysis, I will show you right now, it's definitely visible how inclusion was formed and how it was transformed during our process. So we have experience work with electron furnaces and induction furnaces. We study basic versus acid processes, neutral lining for induction furnaces. We verify effect of aluminum versus aluminum calcium in foundry business, effect of titanium zirconium additions. Some experiments were done with foundry with argon steering in ladle, and mainly our concern was about reoxidation. Reoxidation is a huge phenomenon and difficult to understand today what's going on. Even we prepare very nice, clean steel, and we pour in the mold not the right way. We have reoxidation, and we have defects we also analyze. So we analyze sample collected from different industrial stage. Also we analyze casting defects, and we also use automated inclusion analysis for microporosity. I will show you right now interesting result about not micro porosity. And also we analyze carbide formation. Let me give you briefly a couple industrial examples. Case number one. One Missouri foundry invite us to evaluate steel cleanliness at the induction furnaces, 4,000 pounds, melt, pour sequentially in 100 pounds ladle. This study was done our student Vinci. She is now metallurgist on Newport Corporation. So we collected sample on different stage from induction furnaces before deoxidation. After preliminary deoxidation, they use aluminum star directly induction furnaces. Then we take sample after final deoxidation. They also use titanium additions to gather nitrogen. And we sample on the ladle of the end of pouring and final casting. Vertical axis show total fraction covered by non-metallic inclusion. It seems to be not a big number, but this approximately will be like 0.1%. It's very significant if you talk about percent, or ppm, it will be 1,000 ppm total level. So when we apply automatic inclusion analysis, we can first evaluate fractions of inclusion, how fraction change. You can see, unfortunately, during our process, we have increased area of inclusion. This is not good trend sometimes we have in our industrial practice. Also, we can see size and we can see chemistry. This was important. Nothing happened with sulfur. It's the same because induction furnaces melt in practice, no sulfur change, but significantly change number and chemistry of oxide. Of course, after aluminum treatment, we have blue area, this aluminum oxide. Okay. Also, we have titanium oxide or titanium nitride. Difficult to differentiate, but we have this type of inclusions. And also, we have increased manganese and silica oxide sometimes, which indicate about reoxidation. Problem is, when we did this measurement and discussed with foundry metallurgists, we found that we have not right trend of change in non-metallic inclusion. So after that we discussed, let us to see what we can do with steel cleanliness by changing technology, okay? This is case which I described to you, and this is couple examples when we try different techniques, okay? We use calcium wire injection, we use argon steering, and we use both calcium wire injection and argon steering. It was the same melt from the same furnace, so we have absolutely similar start position. And when you can see that if we apply calcium treatment, okay, we significantly transform chemistry of inclusion. This is before calcium, and after calcium we can see we have aluminum calcium inclusions area, okay, and this inclusion typically liquid. So we have significantly changed chemistry. Unfortunately, this will not help to us. Suddenly we have drop, and then we still have reoxidation, and we have final product also the same trend, increasing amount of inclusion. Then look at argon steering. Argon steering, simple mechanical steering, is nothing changes chemistry, and automated system indicated nothing changed with chemistry. You can see approximately the same ratio between different classes, but number of inclusion did not change and did not significantly go down. But when we apply calcium treatment and argon steering, we completely break this tendency. Instead of increase, we have decrease of amount of non-metallic inclusions, and this was a very interesting result to show that even in small 1,000-pound ladle, we can develop steel which has significantly less amount of non-metallic inclusion, of course, change shape and size. Now we can see what's going on with casting. When we apply different type of calcium treatment, we play game with different amount of calcium wire. We have in our lab portable calcium wire injection. We travel directly in Foundry and produce Foundry experiment applying calcium wire injections. And also we have experiment with steering and with argon steering. Okay, and bottom graph to show non-metallic inclusion in casting according to this different type of processes. And we see the combination of calcium and argon steering allow us, practically speaking, double decrease of number of non-metallic inclusion in steel. Okay, and then Vinci collects samples from all of these heats, did heat treatment, and we started impact energy, Sharpie test at room temperature. And we see definitely correlation between non-metallic inclusions and Sharpie toughness in this steel. Okay, when she plot area of non-metallic inclusion in power minus 1/6 versus Sharpie energy for all this, you have absolutely straight line. And very interesting, this straight line also follow for theory of fracture toughness when theoretically discuss crack propagation from inclusion to inclusion, and this trend definitely we observe in Foundry. Who has interest could look at our articles. We publish this, okay? Application case number 3. One Foundry would like to expand their product on the forge product to substitute casting to forge. So, and this Foundry was equipped with AOD, and we did comparison what will be level of non-metallic inclusion if we use different technology. Simple gravity, sand casting versus centrifugal casting, and look at what will happen. Can we compete or not compete with forged steel produced by vacuum melting? And when we use black columns, this black columns the same in this Foundry, this area covered by inclusion lightly decrease after calcium treatment, but then we have reoxidation and we have more inclusion in the product. Interesting that centrifugal casting technology provide us completely different trend. We have decrease inclusion because we have huge centrifugal forces. And this is a right picture to show what's going on. When we have simple 1G gravity, like we have buoyancy-driven flow, and this calculated flotation time for inclusions 5 micron or 10 microns, we can see that to float inclusion we need a minute, an hour, which is not possible in our Foundry business, and all this inclusion stay in the melt. But when we apply centrifugal forces, which J increase approximately 80 or 100, we have possibility to refine melt by huge centrifugal forces, and this to red line to show that before to pour or during pouring, we can, this is solidification time. Before solidification, we can remove significant part of inclusion. As a result, casting produced by centrifugal method could be significantly more clean than sand casting, and also could be more clean even than forged steel. Now I would like to show you another interesting application of automatic inclusion analysis. We have different features on metal casting. So we have non-metallic inclusion, but also we have so-called microporosity. You can see picture of this. This microporosity between dendrite is the last portion of liquid solidified without possibility to feed. If you look at this picture of a theoretical calculation, what kind of pressure we need to develop to feed this porous, we can see that we need to have huge pressure when we have small pores, and this pressure is not have place in static casting, and then we have microporosity. In centrifugal casting, we have possibility to remove some pore, but also is not possible to remove pore. Okay, this study was done by our grad student. His name was He. Okay, he studied casting from the same Eglin steel received from different foundries, produced by different processes. It was investment casting steel. It was ingot from forge, because in this case we talk about competition between cast and forge product. It was centrifugal casting. And also, we apply so-called heap process, hot isostatic pressure. So he developed special technique allow us to identify, separate microporosity from non-metallic inclusion. And when you see investment casting, you see approximately 50-50 number of micropore versus inclusion. From fraction mechanics, they have a similar, practically similar effect to degrade property. Okay, when we apply heaping process to this casting, of course we did not change inclusion, but we significantly decrease porosity in the casting. Also interesting to mention that this type of microporosity cannot be completely removed even during heaping process. Then we study ingot after hot forge. In hot forge, when we have flow of material during hot deformation, only in this case we can completely heal all pores. And look at here, centrifugal casting. So total amount of inclusion and porosity was less than ingot. Of course, centrifugal casting has some amount of pores, some amount of inclusion, but total amount was significantly less. So I would like to say that modern metal casting processes allow us definitely to compete with forged steel for steel cleanliness. Now let me show you briefly another interesting application. This is about so-called Eglin steel. Eglin steel is a medium carbon, very high strength steel alloyed by chromium and vanadium, chromium, molybdenum, and tungsten, used for specific applications. And our students study property of this steel depending on inclusion number, and found that main trend about carbide detections. Okay, when we have carbide detections, we have significantly less impact energy. This impact energy at -40 Fahrenheit. Okay, so we can definitely do area when we have high impact energy, which require 20, when we have less amount of carbide at 2000, and when we have larger, we don't have enough property. And the problem is that this is carbide very, very small, as less than 1 micron. Typically, automated inclusion analysis is used from 1 micron and above. We develop special technique allow us to detect 0.3 micron of carbide. But to see effect, because they're very small, we need to count 30,000 of inclusion. And when we count 30,000 inclusions, then we zoom out, we start to see what's going on. Okay, every of these points was detected carbide inclusion. And we definitely see that this inclusion were located in interdendritic region. It means they located in segregated area. This was key finding. Then we found technique allowed to produce homogenization, and that final result, we have fine precipitation, remove all of this segregation. So now let me show you a couple other novel techniques which we developed recently in our Steel Research Manufacturing Center. First of all, we developed procedure allow us to have mass balance. So we calculate inclusion area, multiply by inclusion component concentration, and finally we have in ppm level concentration of element of inclusion. So this is very important, because using mass balance we can see where this alumina or calcium travel from the induction furnaces, or magnesium travel to the final product. Okay, and this is an example of steel mill, this log scale. and you can see that total immense concentration significantly would be changed from one steel to another steel. Another important tool, all our inclusion which we observe, this is 2D sections. When we cut, sample, polish, we see something in 2D sections. Of course, what we see in 2D is significantly different than we have 3-dimensional. But unfortunately, 3-dimensional analysis, it's like scan and so on, so it's very, very expensive. So we developed special procedure allow us to recalculate 2-dimensional to 3-dimensional diameter using ASPEX data. And here you can see result how distributed 3D diameters depend from type of inclusion. We can see that all kinds of inclusion has significantly different distribution of size, and this is key important information to understand what's going on. Automatic inclusion analysis provides ton of information. Without that, we have no information. But with automatic inclusion analysis, we have so many information that's so difficult to analyze data. So we try to present a short report which characterizes all inclusion family. In one of the possible tools, so-called joint ternary diagram, every point is inclusion counted. So we count inclusion according to 3 main elements, then we remove that inclusion from consideration for next step. And then we distributed that inclusion to the ternary diagram and put all together. In this case, manganese, sulfur, alumina, sulfur, titanium, and so on, so on. When they put all inclusion, something like this example of stainless steel, we can see all inclusion population. Also, color represents size. And when we see this type of map during processing or compare different steel, we definitely easy to recognize what's going on. For example, in this case, you can see line, this line inclusion, aluminum and magnesium has the same ratio. This is typical for aluminum magnesium spinel. This is ratio at manganese sulfide, and this is something with titanium nitrogen inclusion. So this is tool which we developed today and we use for specific type of analysis. Okay. So finally, very shortly, we introduce concept of inclusion engineering. So this concept of inclusion engineering, it was introduced by Ken Peasley. Unfortunately, he passed away. He was a great metallurgist. This concept includes all type of tools which we can use for inclusion engineering. Start from thermodynamics, like lab graph, simple to show how calcium addition will modify aluminum. Then use computational fluid dynamics to see how inclusion floated, what kind of we have movement, reaction in the melt. And finally, use automated EDS ASPEX analysis, allow us to see what was going before and after. So all of these tools together allow us to produce so-called inclusion engineering and finally improve property of the steel. So let me shortly introduce our Ken Peasley Steel Manufacturing Research Center, which was developed in 2014 in the University of Missouri Rolla. We have certain industrial partners, 7 from main player of steel mill production. We have nice grade for foundry participant, and we have 2 refractory suppliers. So I invite you to consider to come and look at what we are doing in our center and be member of our center. So we have today currently several projects. We have grain refinement during solidification of stainless steel. We have projects about hot working, modern simulations mainly for mini mill. We have very interesting projects which could be interesting for you, non-metallic inclusion engineering for OCTG steel and also for foundry steel. And we also developing third generation of advanced high steel and some specific stuff related to mini mill. If you have interest, please contact Ron O'Malley. He is the director of the center, and we'll be happy to discuss with you. Okay? And finally, okay, Missouri University Science Technology can investigate different steel foundry problems, use automated inclusion analysis. We can produce different type of service. We can help you with sampling. We can help you with evaluation. We can investigate problems, and we determine cause, defect, origin. and we work with you how to develop clean steel. If you have interest, please contact to us, me, Simon Likach, and Zumin, product manager of FEA company. Any questions? This is a list of publications. You will find different our publications. You can look at what we are doing. Okay.
Thank you, Simon and Sumin. We have one question so far, and while I'll read it, I encourage anyone else who has any questions to type it into the question or chat box in their dashboard. But the first question we have is, what measures are taken to account for matrix contribution when analyzing an inclusion?
Sumin?
Okay, so I think the question is about the matrix contribution and its impact on the inclusion composition. Okay, so I think that's a very good question because the matrix does impact the composition of inclusions. Right? So right now, the technology we developed is to increase the X-ray takeoff angle. So when the X-ray is generated inside the matrix, it has, because the takeoff angle is higher, as typically around 45 degrees compared to traditionally 35 degrees takeoff angle. So the X-ray will travel in a shorter distance in the matrix. So the matrix effect is less. But the matrix effect is always there for the EDS analysis because of the way the X-ray is generated. So yep. There has not been a way to eliminate that effect.
Okay, but okay, we also apply so-called zero-element rules. So when we have spectrum, and spectrum has a matrix, so we apply rules which move out a matrix. Let's say that iron more than 10%, we assume that iron equals 0, all other elements equal 100%. This allows us to evaluate inclusion versus oxidation area or versus porosity. So apply additional software tool, we can classify inclusions versus porosity or versus stain. Of course, we have some matrix effect, but we try to minimize this matrix effect. What problem we did not solve today, we cannot analyze pure iron oxide. This is no problem to classify pure iron oxide from our side. So all another oxide or sulfide, we can easily classify using this system.
All right, we have one more question. Do you see this useful in a ductile iron foundry?
Oh, good question, because I am ductile iron guy. Okay, we used automatic visual analysis for several different directions for ductile iron. First of all, ACM analysis allows us to collect absolutely right data about spherical graphite population. When we use optical analysis, we cannot differentiate small graphite inclusion versus non-metallic inclusion. So when we use standard procedure for evaluation of nodule count or nodule size using optical system, we typically ignore small particles. We remove particles visible less than 4 micron typically, and we consider only large particles. But small particle is crucially important. In some technique, inoculation technique, we develop small graphite particle at last moment of solidification, and these particles significantly affected on perlite ferrite formation. So to ignore this information, we completely lost most important information. By applying automated inclusion analysis, we collected all spectrum of inclusion, and I have a couple articles presented in American Foundry Society. More interesting another application. So when we use so-called soft quenching technique, we collect sample from the melt, and soft quench allow us to have very small graphite inclusion, and then we applied automatic inclusion analysis to analyze what will be nuclei inside. And we found very interesting average composition of inclusion inside nuclei, inside graphite. This was key important factor to develop new inoculant, because we definitely know which inclusion inside graphite or which inclusion could be outside in metal matrix. So it could be different type of interesting applications and for ductile iron production.
Very good. I have another question that came in. The analysis discussed applies to mounted and polished samples, which represent very little surface area of the steel heat, being usually in a range of 10 to 50 tons. Do you think such type of analysis would be possible to be applied in the future as part of 3D X-ray tomography, which could be used for 100% of the steel volume as a part of the final inspection process?
Yeah, the perfect question. Okay, no one tool could be solve all problem. Definitely, when we analyze a couple millimeters square from 100 ton of liquid steel, it's the same time as it analyze one person from the whole world population. It's approximately the same ratio. But all people different, and we can say that our analysis was not consistent. But when we have liquid steel, we have good mixings inside liquid steel, and typically when we start to count more than thousands of inclusion, we use so-called a random technique, when we polish larger area and took inclusion randomly from different area, which allow us to have consistent result. And I would like to say that this method definitely to present a real situation with some, of course, variations. Okay, but other methods which could be used for mapping of three-dimensional, of course, is very important. But today, that method, I will consider like macro. We don't have any technique allow go to less than 50 micron. But we talk today about inclusions with range from 1 to 10 microns. Zoom in? Any additions?
I think, yeah, like Simon said, different techniques are used for different purposes. And for the sampling of a steel from a large ladle or whatever container, the sampling is important. Right? So what we've seen that in steel mills, as long as the sampling procedure is consistent, the analysis results are usually repeatable. Right? And that's why this technique has got a very wide adoption in the steel mills for the improvement of steel cleanliness.
Yeah, we study stability of our results when we use different sampler, when we different cut of the sampler, when we use different polishing media, and we use different FEA setting, because we have different type of setting. So we now prepare special articles about inclusion analysis technique and how setting, polishing, and sampling affected on result. This article will be presented in next AIST conference, and you can find information that we did a lot of our students, a lot of study to see how stable our results from analysis.
All right, we'll do one more question before we close the webinar. And the final question is, how would you recommend gathering quantitative NMI data if you are limited to a light and inverted microscope?
Zoom in.
Well, so I guess the question is about using a light microscope, how to get quantitative data. I think as the light microscope stands today, it does a good job of detecting inclusions, but it doesn't provide the chemical composition of the inclusions. And without that critical information, it's really difficult to control and modify and engineer the inclusions to meet the specific needs in either steel mills or foundries. So I don't have a good answer on how to optimize the quantification of inclusion data for the optical microscope.
Yes, I will say we need both methods, because in foundry business we need also to see structure. Okay, what is the structure? Without optical microscope we cannot see general microstructure. So I believe we need to have both tools, and all of these tools, scanning electron microscope with automatic feature and optical microscope old-fashioned, could be very helpful when they go work together. Sometimes we, in optical microscope, we observe specific areas, and we go to SEM and to look at what's going on with specific area, because sometimes inclusion could affect it on microstructure. So we can see after specific heat treatment, like aciclovferrite and so on, kinetic of this reaction significantly depend on inclusion composition. So first look at optical microscope, then we look at scanning electron microscope, and then we verify what's going on with property of material. So I will use both, my answer.
Very good. And thank you again, Simon and Sumin, for the webinar presentation today, and to everyone else who joined us. Have a great rest of your Tuesday.
Hey, thank you.
Thank you.